All right, so today we are moving on to concavity and inflection points. Concavity is used to describe the way that a curve bends. For any 2 points in a given interval that lie on a curve, if the segment that connects them is above the curve, then the curve is said to be concave up over the given interval. If the segment is below the curve, then the curve is said to be concave down over the interval. I'll give you some time to write that. This will all make more sense too whenever you actually see a picture of what we're talking about. A straight line is neither concave up nor concave down, and a point where the curve changes its concavity is called the inflection point. Okay, so when we look at these graphs, we can determine the concavity based on the line segment that connects 2 points. So this is our graph in red, right? And the line segment that's drawn between the 2 points is above the red line, right? So if we look back at our definition, it said that if it is above the line, the segment that connects any 2 points, if that is above the line, then it makes it concave up. You can forget all the squiggles. So that's concave up. This one, the segment that connects 2 points, is below the line, so that would be concave down. In a lot of cases, you can look at it and kind of see whether it's concave up or down, even without the line. Like if I look at this, it kind of reminds me of a cup, right? Or a bowl. And if it could hold water, it's concave up. If it can't hold water, it's concave down. This is kind of the shape of a bowl. If I put a little lid on here, it's like a little Tupperware. Yes, there is. Yes, sir. Here we have a graph that is concave down for half of it, and then it's concave up over here. See, it's like the cup is upside down, and over here it's like a cup is right side up. So the point in the middle where it switches from concave down to concave up is our inflection point. Analyzing a graph. So first we graph this function, and then we're going to estimate the following using the graph and a max and min finder. So we're going to find all local max and min of the function. Then we're going to find where it's increasing and decreasing, all the inflection points of the function, and the intervals where the function is concave up and where it's concave down. All right, so in order to do this, what we have to do is plot this. We're going to put this in Desmos just because it's convenient for us. So whenever we put this into Desmos, let's see how good my memory is. Negative 2x to the third, not very good, plus 6x squared minus x plus 3. So now whenever I look at this graph, it's nice because, again, I have my lowest points marked for me and my highest point marked for me. So it says find all local max and minima. So that's my max, 1.913 and 9.043. In my min, is this point here. As soon as I stop drawing. So 0.087, 2.957. So that's my min. Since the intervals where the function is increasing and where it's decreasing, let's be smart about this. So that was my max. My min. Dang. Did you guys just hear my door get banged on? Nailed it. 0.087, 2.957. All right, where it's increasing and decreasing for part B, it's decreasing all the way from negative infinity to here, which is 0.087. And increasing from 0.087 till it hits the max. Which is 1.913. And then decreasing again from 1.913 to infinity. And then we will finish parts C and D tomorrow.